Good afternoon, good morning, good evening, everyone. My name is Carmen Guguta, and I'm your host today from Technobis Crystallization Systems. Welcome to our webinar on the Crystal16 as a multifunctional tool for solubility, solid form screening, and crystallization process development. A webinar presented today, brought to you today with the help of Crystal, Dr. Mihaela Pop. Just before we start, I would like to share with you a few technical details about this webinar. It's being recorded and is going to be made available to you. The recording somewhere tomorrow, you will receive an email with the recording and a link to where you can download or have access to the slides of Mihaela today. If you have a question, please make use of the chat function of this webinar platform and write to us or send an email to info@crystallizationsystems.com, and we will do our best to answer your questions as well. I think Mihaela will share also her email address, so if you would like to contact her directly, it's also possible also to write to us. We will make sure that she receives all the questions that you are sharing with us. Before we just start with introducing our presenter today and going on with her presentation, I would like you to, for those that they do not know, Technobis, to introduce you shortly our company. Technobis Crystallization Systems is a Dutch company located in the north of the Netherlands in Alkmaar. We are a world-leading technology provider for solid-state research, process development, and formulation. We are on the market since 2005 with more than 600 instruments installed worldwide since that time. In our portfolio, oh, my slides are not going. Oh, sorry. Sorry for this. Our portfolio, as mentioned, in our portfolio, we have three products: the Crystal Breeder, Crystal16, and Crystal9 instruments. Some of you might already know or already have in their lab the Crystal16 or the Crystal9 instrument, or both of them. If after this webinar you would like to test one of our instruments, or either to know a bit more about it, you can contact us either via the website, either write to us at info@crystallizationsystems.com. Just before that, I would like also to mention that the Crystal16, remember, is the instrument for solubility, metastable zone with solid state screening, the Crystal9 with the camera technology, and that works exactly like a microscope, and the Raman connection. So if you have a Raman spectrometer in your lab, you can easily connect it to this Crystal9 instrument. Helps you to develop or optimize your crystallization or formulation process. While you are performing the experiments, you can really see what is really happening in your vial. You can follow polymorphic transformations or even chemical reactions. The Crystal Breeder, the lower volume instrument that we are marketing, with its vapor diffusion setup and controlled evaporation setups, is our gadget type of instrument, as I like to call it, is the instrument to be used in growing single crystal or perform crystallization type of screen. Technobis manufactures, as I mentioned, lab instruments which enables you to measure, characterize, control different crystallization related parameters. And I'm pretty sure about the Crystal16 you'll hear more today. What you see on this slide is the latest version that we have launched last year, in the beginning of the year, the Crystal16 version 3. With a totally new software. And next to it is the Crystal9 version 2 that we have launched last November. Standard instrument that comes now standard with 8 cameras, and a new software that allows you to detect characterize the particle shape, determine particle size of the materials that you are working with. And this is it. This was about our instruments. Now I'm coming to our speaker today, Dr. Mihaela Pop. Mihaela, we know each other for quite some time now. We go back to the Avantium time. I'm happy that we could host and bring this webinar together today to our customers, our viewers today. A bit about Mihaela. She has more than 20 years. I think we just were talking now much more than 20 years of experience in solid state chemistry. She has received her PhD from the University of Cluj in Romania, moved to for her postdoc to University Amsterdam, and then where I actually also met Mihaela. She moved to Avantium, maybe a company, a CRO known to some of you attending today this webinar. Since 2013, Mihaela is the Chief Scientific Officer of TerraCrystal, a CRO that currently oversees the entire scientific research and technological operations of the CRO. Her scientific expertise is enriched by substantial experience in development, implementing, and promoting of new concepts related with crystal form investigations. And many compounds that pass through your hands. I dare to say thousands of them that pass through your hands, through the ears, Mihaela.
Once still again, surprising, all surprising still.
Yes. Thank you very much for joining us, for making this webinar available for our viewers today. I'm going to make you the presenter today. I hope everything goes okay. And I give the floor to you.
Thank you very much, Carmen. Let me see if it's not working properly. Just a moment.
We'll also take off my camera, so I will allow you.
Screen, right? I have to share. So I'm not sure if, can you see my screen, everybody? Carmen, can you see my screen?
I see your screen and I see, but not the presentation mode. I see the other one like
that. So now you see the presentation mode.
Now we see the presentation, indeed. Perfect.
Okay.
Yes.
And I will also just give me a moment. Yes. Okay. So good afternoon, good morning, everybody. So today, as Carmen, thank you very much for the introduction. I will try to share with you my experience in using Crystal16, the way and the shape it looks now, which is really developed and very nice tool compared to when it started. And I think I was actually there when the Crystal16 was developed, but this is incredible advancement in development of the tool, and it was a pleasure for me to work with it. So I will try to share the experience in determining solubility, solid form screening, and also how we approach crystallization process development with Crystal16. First, I will give you a very short introduction regarding TerraCrystal, and then go on regarding solid form screening, solubility, and process development. And I will talk generally about them, but also highlight our findings with some case studies, and I will end up with the conclusions. So a little bit more about TerraCrystal. Already Carmen touched on that. We are an independent CRO focused on solid state chemistry and crystallization process development services for our customers. we were incorporated by 2 former Avantium employees, and we are having expertise in crystallization and polymorphism. And our purpose is to pursue top quality science and for our customers, and to balance this with needs and also with a commercial potential. We can do that by combining experimental know-how, strong experimental know-how, as Carmen mentioned, having the chance of working on multiple compounds and diverse compounds, but also combining this know-how with modeling tools, crystallography, and advanced analytics. So in each and our project, we target a flexible approach, and we try to tailor it as much as possible to the needs of the customer, but also to the properties of each and every compound. And last but not least, our philosophy is to maximize success by intelligent experimental design. And basically, this combines all what I've said before, combining all our knowledge and all our expertise in getting success for our customers and creating value for them. And I will start regarding solid form screening and why this is so old and also so actual, more than 20 years, as Carmen mentioned. So it is quite important because, first of all, many compounds are exhibiting polymorphism. And because this is not only about polymorphism, but it extends to multi-component solid forms like salts, crystals, which are increasingly important. So as many of our compounds under study are pharmaceutical compounds, we all know that about 90% of them are polymorphic. But if we look in the Cambridge Structural Database, which already now up to date has more than 1 million crystal structures determined, and if we look at organic crystals, so crystals of organic compounds, we see that already 65% have polymorphs and determined structures, so confirmed, let's say, polymorphs. And 9% there are having small changes in the crystal structures, which are not true polymorphs, but due to temperature or pressure changes, which changes, let's say, the crystal structure. So 65% definitely from all the determined crystals of organic compounds are polymorphic. So that's a reason to address this for the compounds, organic compounds, but not only to that, but to mitigate, let's say, the risk or to control the polymorph that you want, but also the fact that each solid form will have potential different physico-chemical properties, and by knowing all the forms, by knowing their properties, then you have a broad range of choice of properties for a specific application. And that makes it very interesting, not only for pharma industry, but also for agrochemicals and food industry as well. So that's why solid form screening is very important. And it seems, well, we just screen, but it is quite complex, because screening nowadays is quite challenging in identifying everything what is there. So the whole landscape of solid forms, and as I mentioned, is not only polymorphs, but also multi-component solid forms. And after you identify them, or we identify them, it's a question of selection. So what is the application? You need really to understand very well what for you choose a certain form. So that can be quite labor intensive in terms of analytical techniques and deciding, actually building a characterization strategy and very clear criteria of selection. So screening, landscape, selection, also quite some challenges. And afterwards, after you select one, or let's say the lead form and the backup one, then you also need to produce it at larger scale. So to develop a crystallization process, usually, mostly, sometimes also to stabilize amorphous, but that's another subject. So now we talk about crystallization, and so build a crystallization process which is robust and which can be transferred then to production. So solid form screening is very actual and still a puzzle, and the starting point can be every time different depending on time constraints, customer application, and so forth. But when we screen, always solubility comes into play, and not only when we screen, but also when we develop a process, and also when we characterize the solid forms that we find. So that's why I wanted to show you the 3 types, let's say, the most common ways of determining solubility. And one of the method is just changing the composition, so having a certain amount of solid and adding small amounts of solvent, and then looking, can be visually or by using turbidity, and just see if it is dissolved or not. So you get a rough solubility indication, but this can be sometimes useful when you design the next step in the screening for identifying all the solid forms. Then you have solubility with the temperature. So by increasing temperature, you determine the point where the solution takes place, and this is detected usually by turbidity, and this is what Crystal16 is using. And that is a nice tool because you at a sudden determine, by using different concentrations, you can determine solubility curve, and then by cooling also in a controlled fashion, you see if you have a crystallization or a precipitation of your solid. So you can get 2-in-1 solubility and crystallization information. And if you are lucky and you get concentrations where you can get more points, then you also can have an idea what is the metastable zone with already in the first experimentation phase. So that is quite handy when you later on will design a crystallization process, because this is an information that is encapsulated from your initial solubility screen, let's say. And then the last one, which is the most accurate, is equilibrium solubility, which usually we determined at the end when you find different solid forms and you would like to compare their solubility, and then you really need accurate values. It is more time consuming, but at that stage it is worth it, because that will be your selection criteria in some cases. So this is the setups of solubility and using them. And as I mentioned, Crystal16 offers this extra information, which I will show you later in the case studies, is quite useful. And now for the crystallization process, I just made a small, quick scheme just to give you an overview on what comes into play in a scale-up program. So in a scale-up program, we go, first of all, we want to find a process, to develop a crystallization process, so a route selection. And for that, screening data is quite important. It can be polymer screen or other type of screening data, but there, as you searched a bit broader, then you can select what are solvents, but also behavior with respect to crystallization in certain solvents that you would like later on to translate into a process. So these are 2 important things: looking at the data, choosing few solvents, even build in this solvent selection some diversity such that you decrease the risk of ending with no process. So these 2 points, and then for those solvents that you selected based on already knowledge from the screen, you would evaluate cooling, anti-solvent crystallization, or a mixture of that, determine metastable zone width, and then in the end look also at the solids, and then based on these 3 things, hopefully you will be able to have a process, and then you will go on to scale it up and to test robustness of your process at larger scale. So now coming to solvent selection, just to make it a bit more visual. as I mentioned, by doing screening and using Crystal16 in screening, you already have captured some information on the metastable zone width. And this is quite, even if it is not complete, because you don't have maybe 4 points on the nucleation line, but still you have an idea, even for a certain concentration, what is the width of your metastable zone. So that is quite important in moving faster towards developing a process. So we look at solubility in the process development, metastable zone width, which will tell you also something about the yield, and then characterization of the resulting solids will give you information on purity and particle morphology and also particle size distribution. So as an example, I can show you here from the compound, which has a very strong tendency to form thin needles. And then based on the screen, only few solvents or conditions led to granular morphology. Then obviously you will take those conditions and then you will develop metastable zone width and a crystallization process. Maybe some just a side information on analytics that can be done nowadays. Also in terms of analytical capabilities, there are huge developments. So you can, if you see a granule, you can even map if it is a salt, like a sodium salt in this case, you can already see the distribution of sodium on a particle by using scanning electron microscopy and EDX, for instance. So this is very nice to have, but it doesn't have to be applied for every. I mean, for the needles, you will not need that. But when it comes to the product that you would like to develop, then you need to make sure that all these granules, that the distribution is fine. So that's about solvent selection. And then, as mentioned, scalability and robustness means an increase in the scale of crystallization from 500 mg to 110 mg and then 100 gram scales for a robustness check. And usually what we do, the variables that we investigate are the seeding. Again, metastable zone width, very important to have as soon as possible. Then heat transfer, stirring, filtration, as you might all be aware of, washing, drying. And the output parameters.
Hello?
Yeah.
Sorry for interrupting you. We do not see the slides anymore.
Oh, really?
Can you try to share again?
Ooh, which, yeah, okay. Which slide do you see?
I see only us.
Oh, okay. Just a moment. Share. Oh. Oh, share again. Just a moment.
Yeah.
So do you see now?
I see the slides, but not the presentation mode.
Okay. So, yeah, which was the last slide, Carmen, that you saw? Is it this one?
I don't see anything moving. Yeah, this. Yeah.
Okay, so this one? All
yes,
right.
perfect.
Oh, I'm sorry, I don't know.
Yeah, I don't know also what happens.
I said something wrong, I think.
Could be, I don't know.
So you see my pointer as well?
Yes. Okay. Perfect. Thank you.
All right. Yeah, so as just mentioned, then for analytical capabilities, it's quite important that at the moment that you identified the particle morphology, particle size, and you have the process that you want, then you also can look into a very huge detail how things are in your product, how, for instance, sodium is distributed in certain particles. So in terms of process scalability, probably you heard me, but you didn't see the slide. So we go to larger scale. We look at seeding, where metastable zone width is quite important because you need to seed in this metastable zone width, but also the heat transfer, while you increase the scale, stirring, filtration, washing procedure, and drying conditions, and trying to vary this and to check the output parameters, namely polymorphic form, if it is unchanged, morphology, particle size distribution, the yield, and the chemical purity. So you can imagine that by having a good starting point in terms of process that you develop, that has more chance to have a scale-up process where no problems will take place. And this brings me to the case studies, where I will share with you how we used Crystal16 basically to build certain screening strategies, but also to develop processes for crystallization. And the first case study is about MCPA, which is a broad spectrum leaf herbicide, and it's approved in EU, USA, China, and Australia, and produced huge amounts. So you see that it's a matter of hundreds of millions of kilos up to 2016. So you can imagine that for these agrochemicals, the need, because of production at such a large amount, the need for a crystallization process is continuous because of improvement of the yield, for instance, but also to decrease the costs. So then we looked at this compound, and we looked in different solvents for solubility as a starting point to, as I mentioned, to every screening or process development. So what we noticed, our first observation was that it's really huge solubility in the pure solvents. So immediately after one Crystal16 run, we decided that we need to look into solvent anti-solvent mixtures. And then you see here the solubility curves in different solvent heptane mixtures. And already here this gives you an overview and a selection possibility. And in this case, the obvious selection was ethyl acetate heptane, because we expected quite high yield without the need to cool too low. So, and also fulfill to our initial desire to decrease a bit the solubility such that we achieve a good crystallization. So that was the solvent that we decided to move further. And what we did, we varied further ethyl acetate heptane mixtures in two ratios, so 20/80 and 50/50, and also compared to the pure ethyl acetate. And so you see here the solubility curves. And we decided, still due to the high yield for the 20/80 mixture, we decided to determine also the metastable zone width for this mixture. And then you see here, we did 2 cycles of heating, cooling, and turbidity measurement. So different concentrations, actually 4 to 6 concentrations. And then in 4 to 8 hours, we were ready with metastable zone width. But definitely you see it is quite narrow. So that was still not perfect. And well, then looking at different ratios between solvent and anti-solvent, you can imagine that further, maybe a second step of optimization would be necessary if you want to be safe with respect to the width of the metastable zone and such that you can control, for instance, the particle size distribution. So by further optimization, you would definitely in this system be able to develop an effective crystallization process. But also for this compound, then the next step was, okay, we knew that in ethyl acetate heptane, a nice crystallization can be developed, but then we were wondering if we can grow crystals. So you see here was the starting material as was purchased, and then we wanted to have a broader metastable zone width. So for that we chose another solvent system. So it was 2-propanol heptane. And then we saw, yes, the metastable zone width is broader in this case for a certain concentration. And what we did thermocycling in the metastable zone width for a few cycles, and we saw really beautiful growth of the crystals, and even very nice crystals suitable for crystal structure, single crystal and crystal structure analysis. So you see that the same tool can be used in a different manner, and it is very nice if you have built already solubility data and metastable zone width of different systems. Then you can use one system for a process development and another system for crystal growth, like in this case. Then another case study was also on agrochemical compound, and that was 2,4-D is called, 2,4-dichlorophenolic acid. And this is a more selective leaf herbicide. And what we saw here again, it was this very huge solubility. And you can see it already here that, the compound, as soon as you drop it into a solvent, it goes immediately into solution. And then even if you cool and then you heat cool and you try nothing, it's still a clear solution. So transmissivity is 100%. So this huge solubility was found, and also fast dissolution basically was in most of the solvents, but ethyl acetate in this case showed crystallization, and then we determined the metastable zone width. You see only 3 points, but we had an idea that there is precipitation for this concentration range. So therefore, although this was done for a parent compound, we decided, okay, ethyl acetate should work probably also when we want to make salts, and maybe in the setup of a salt, then we could build a crystallization process. So we chose ethyl acetate and then screened for different salts, because as mentioned, due to this high solubility, in order to have a screening for salts, which would give you also a potential crystallization process, cooling crystallization process, was quite challenging. So not many solvents fulfill this criteria. But in ethyl acetate, that was very nice. So we screened multiple counter ions. And here I show you the example with diethylamine salt. Also here we applied 3 heating cooling cycles in Crystal16. And you see, this is an interesting thing, that what we observed at the first cycle, we saw some noisy turbidity signal. And also the metastable zone width was different than in the next 2 cycles. So the conclusion was that we didn't characterize exactly here, but it was, well, probably the first cycle is this noisy signal is an indication that probably not complete salt formation took place. So you had also other precipitation effects, but here salt formation took place, and then you can from the second cycle, basically we were recrystallizing the salt. So here we had a very constant metastable zone width, indicating that here we have another entity. And probably you are familiar with this when you see changes by cycling, by doing multiple cycle with Crystal16, can be an indication of different polymorph, or in this case, salt formation and salt crystallization later on. So therefore, the strategy for salt screening, our strategy was to use more cycling in Crystal16. And that was successful, and you see here the different melting of the salt that we made with the ethylamine. And this brings me now to co-crystallization. And for co-crystallization, we also wanted to see how we can best or efficiently use Crystal16 for screening. And you know, for co-crystallization, that screening is a little bit different in terms of design. So a lot more time is spent in looking what are the right molecules, so-called coformers, which will match with your active or with your parent compound such that they will form together a new crystal structure. And in this case, I have to, for salts, it's quite easy because you based it on an ionic interaction and pKa difference. But here, it is really an advice to spend time on looking at the literature, but also structural databases like CSD, use predictive algorithm, look at likelihood of hydrogen bonding and so forth before going to experimentation. And so we did that. And then, our strategy was, after having a design of experiments, especially in terms of coformers, which could match with a certain compound, then we thought of an experimental strategy which would create enough diversity, but also be very fast and give the high probability of finding new co-crystals. So in one run of what we did, we split the runs of Crystal16 per coformer. So in one Crystal16 run, we applied 2 methods. So for each method, 2 different solvents and 4 concentrations per solvent. And that was quite nice because in the solution method, which is a method where ideally all the components, the 2 components are in solution, and then you achieve crystallization like you see here. So you get everything in solution, and then you get crystallization. And then, as I mentioned, for the salts here also, we run 3 cycles. But the nice thing is that here you already get, as for the salts, information on the metastable zone width, and if something happens, maybe that is not always the same. And I will come back to that later. What does it mean? But by using more solvents and more concentrations, then you have extra information from turbidity. And in the slurry method, the turbidity signal was used just to monitor that, well, there is constant slurry. So you see that transmissivity is 0 all the time during the experiment. And the temperature was kept constant. So this was our strategy for co-crystal screening per coformer. And as I mentioned, in the solution method, like you see here in the table, the first items and then the slurry method. But for the solution method, the fact that the metastable zone width was relatively stable along the cycles, the heating and cooling cycles, that already provided the metastable zone width by having also multiple concentrations, as mentioned, in a run, but also showed that we are most probably in this particular solvent having a congruent system. And the congruent system means that the co-crystal, when it dissolves in the dissolution, there are no secondary solid forms crystallizing. So it is really an entity, and there are stoichiometric, there is a stoichiometric relationship which is maintained in the behavior in solution. And this is what we want, because then by having a congruent system, and I will explain you a little bit later what it means to have an incongruent system, that is more trouble in process development. So this is what we are looking for. So if we screen broad enough in terms of solvents, in terms of methods, and we identify congruent system, then we are really really safe with the co-crystallization process development. And you see here, so in the solution method, we find the same pattern. Also in the slurry method, the same pattern. So that means that you have very, very low chance of getting crystallization of the components. As mentioned, this is quite an important add-on when you have this information at the screening stage, because you already, after the screening, you know, okay, these are the conditions for a congruent system. So after having the co-crystals, as I mentioned, you need to characterize, and the typical methods are, besides X-ray, which identify the identity of a new solid form. It is the melting, but also solubility or dissolution rate. So you see here in one example where you have a high melting co-crystal compared to the parent compound and still a higher solubility of the co-crystal. So that can be, it's not necessarily that a higher melting will mean lower solubility. Regarding congruent system, as you saw just yet, it is quite nice because also you are safe in trying to grow crystals of the co-crystal. Otherwise, you may always run into maybe crystallization of the components. So that will be a next step when you have such a co-crystal and in a congruent setting. Some more examples on co-crystals of agrochemical compound, another agrochemical compound. So you see this is the X-ray of the parent compound. And as I mentioned, when you look for co-crystals and you run your Crystal16 cycles and you see it's a congruent system, you analyze first by X-ray, but be careful and look at all the polymorphs that the parent compound, but also that the co-former, in this case fumaric acid, might have. So here I represent just one, but comparison should be made properly, and then you assess the new co-crystal, and then DSC will further confirm that it is a completely unique new entity, as the melting point in this case is higher than the polymorphs of the parent compound. So that's example of one co-crystal that we found by using this strategy with a Crystal16 in one run, and another co-crystal with 3,5-dihydroxybenzoic acid. Again, comparison. Here we also did, you see here preferred orientation, we also did crystal growth afterwards by identifying congruent system and solvent in which this is formed. Then we did also extra cycles in metastable zone with, and then we got preferred orientation of really big crystals. Yeah, so in this case, you see that the DSC shows a lower melting. So as I mentioned, if you compare with the previous slide, yeah, you see that from 140 more or less, and then 70. So you can really modulate your properties a lot by co-crystallization, which makes it so interesting in different applications. And well, I promised you I will come back to incongruent systems. So this is, let's say, the thermodynamics of co-crystallization. When you really want to understand and control and to build a process for co-crystallization, you really need to start, the starting point is on building the ternary phase diagram. And you will not do it for each and every co-crystal, obviously, because it's quite labor intensive, but for the ones of interest, that's definitely required. And yeah, it will give you a predictable process. So this is the congruent system, which we all want. And if you identified it from the screen, is fantastic. So there are basically, this is the co-crystal region, and there are no secondary solid phases. If you perform a dissolution in a, you increase basically the solvent amount. So you really don't cross other lines. While if you go, in this case, you see that you cross also other lines. So you are not only in this co-crystal region. So here, for an incongruent system, is basically when other solid phase can crystallize when you dissolve the co-crystal. And this happens usually when the solubility of the two components are very different. While here, when the solubility is similar, and you see the solubility points of A and B, it's more or less in molar. In molar solubilities are more or less the same. While here, if they are very different, like you see here and here, then this region will not be anymore in the congruent setting. So phase diagram is absolutely very important. And you can also You can build it by doing all the solubility information, you know, the solubility curves of the components and the mixtures, and then to build it point by point, or you can just determine the critical points, like the eutectic points, like you see here, where the liquid is in equilibrium with the different solid phases. Here, co-crystal and, let's say, component A, and here, co-crystal and component B. So you can also do that, or you can just, sorry, I have to go back a little bit. So what I also show you here, it is what type of crystallization and where you are. So by having the ternary phase diagram, you know how you can approach your co-crystal region. So for solution crystallization, like I showed you we did with Crystal16 in a screening fashion at that point, you basically start in the region 1, which is where both components are dissolved. So they are in solution, and then you just go towards, let's say, the co-crystal region. Then you have the reaction crystallization, in which you start with dissolved higher soluble component, in this case B. So you start with this, and then you add the component A, such that you move from this area from 1 to 4. Then you have the slurry, and which is the blue and the yellow. So depending on what concentration you choose, like you see here, you cut it. So you do different slurries at a certain temperature, and then you already have an idea, okay, am I around the stoichiometric ratio between the components? So am I around the congruent, let's say, region or not? This is the slurry part, and then you have the grinding, where you don't have almost no solvent, just a few drops, and then you are basically here. So you almost get rid of the third component as solvent. What I wanted to show you is really that having this congruent situation is really very nice and makes life a lot easier, but you can also build it in a simplified fashion by running slurries and then determining what solid forms for what composition, and then also determine the solubilities of the components, and then derive from that the eutectic points. So that is important for co-crystallization process development. And this brings me to conclusions. So I hope I gave you an idea how we use Crystal16 and in an effective manner for screening, for novel forms, from polymorphs to complex and multi-component solid forms, up to crystallization process development. Also how we start by looking at solubility in different solvents, and get also, as much as possible or when possible, the metastable zone determination with Crystal16, because this will give us then a better grip on experimental design and also how we grow crystals, for instance. But I think the most important experience with Crystal16 was co-crystallization, and the fact that by having this information of metastable zone width at a different cycle, then enables actually to identify congruent systems, which are very important for later development of the co-crystals. So I think, well, I hope I triggered you to use Crystal16 and to think of ways of applying all these tools for your crystallization research. So in the end, I would like to thank, first of all, Technobis for this opportunity and for the very nice collaboration. And especially I would like to thank Thomas, Dan Dumitrescu, and Carmen for a very nice collaboration on these case studies and a good partnership. And I would like to thank you for your attention.
Thank you very much, Michaela. And to your girls in the lab, they have performed quite a lot of this work.
We enjoyed it. It was very nice.
Yes, thank you very much. We do have quite a number of questions, so I will start jumping into them to try
Very
to
good.
answer as much
I
as
didn't take too long, right?
No,
Oh.
no, it was perfect.
Okay.
So I will start, Michaela, if you're okay with that. Yes?
Yes, please.
So we have a question. So for a completely unknown compound, what mass of compound would you need to understand the solubility in 16 solvents? How much solvent and how much compound would be in each vial? So you have a totally new compound.
I have to do now design in 1 minute.
I think what we always say is try to do a test visually and see, assess how much you could add until you make a slurry. So then it gives you already a bit of an indication.
So what we typically, I can answer what we did with these compounds, for instance. We typically, as you say, we start with a slurry. So usually we start, 16. We don't know, of course, how the solubility will be, but we need to start with a slurry. So those 16 solvents should give slurry within the volume of Crystal16 in this case. Otherwise, you will need to add another to have mixtures. But you will start with, let's say between 15 milligrams up to, you can also do up to 100 milligrams of compound per vial, depending on the solubility. And you start with a slurry. So I would say for 16, if I do a rough, probably 16 times 10, let's say 200 milligrams, probably we could have that.
Yeah. Another question from Judith. How much material was crystallized in each experiment in the Cocrystal screening?
I think I had a slide where I even showed the vials. Sorry, now you will. I'm still sharing, Carmen? Yes. Huh?
Yes.
I hope. Yes, probably. Yes, here. Yeah, so here, well, maybe now it's not so beautiful visible, but I can make this smaller. Yeah, so you can see here, we had about 50 milligrams, I think. 50 milligrams per vial. Yeah. And this is, very good question. Thank you. Because when you have this congruent system, it's beautiful because you can get it from solution and from slurry, and then no problem for characterization, really. So from the screening stage, you can have DSC, you can have dissolution, solubility. Remember the solubility, the equilibrium solubility that we are talking, that you want to determine very accurately, but you can even grow afterwards because you know already the metastable zone width. So you can take this material and then grow your crystal, and then you are in this situation and determine the structure. This is what we do. So
yeah, nice, beautiful. The solubility values of 5 degrees, are they experimentally measured? Example, in the second and third cycle, or extrapolated using the fitting equation?
Very good question. Thank you, Thomas. With a new software, which I didn't use, I have to say, he extrapolated for 5 degrees. Yes, that's
Indeed. So this is a new feature of the new software of the Crystal16 version 3. Unfortunately, you had version 2 in your lab.
Yes. And also here, it was extrapolated, I think, in 50-50. So we had a 2080, but with the new software, he extrapolated where the 50-50 would be the solubility. And then that's where actually you could also maybe extrapolate a little bit, I don't know, maybe 30-70, and then you would get a broader metastable zone. Maybe this is a subject for further, let's say, and to check also experimentally if it fits. That's a nice idea, maybe.
And now thinking a bit, getting a bit nostalgic, I must be sincere. So thinking the very first time I worked with the Crystal16 version 1, do you remember we had it around all those with the glass plate and so, and the software. Now thinking of the software, it was a bit not that user friendly, to be sincere, when you are making the program. And so I always had to think extra on how to you make an experiment. If I missed something, I didn't do it right, then you had to redo everything again, re-prepare your samples. These things, we do not have them now with the version of the second version or even the third version. Now the third version comes with all these analyses and tools that multi-analysis, what we call it, that really helps you. By a few clicks you get quite a lot of information out of it. So it's still nice to see this. Okay, I talk a lot. Let me go to the next question. I have a question related to the single crystal growth discussed on slide 12. I think you mentioned that the thermal cycling within the metastable zone was used to get the single crystal. Does this match the temperature versus time in the diagram shown in the slide? I ask because it looks like to me that the temperature cycles well above and below the metastable zone. If not, can you expand on the temperature cycling method used to get these nice crystals? Example, number of cycles, temperature range.
Yeah, well, I have to say here, I just took it for example purpose. So it could be that it doesn't match exactly, but what we basically do, if I find a metastable zone, which is nicer, let me see, in the beginning maybe. Oh, here. Yeah, I don't find it now very easy. Here, yeah. Yeah, so indeed you have to stay depending on, I will have to check how many cycles, but of course you don't want to degrade your compound. So usually up to 5 cycles we used to do, but we, for a certain concentration, so depending on the metastable zone width, usually we would prefer a broad metastable zone width, but not at very high temperature, such that we can run more cycles. So let's say here, you would be, here it's quite high, the concentration, but if you would go lower, then you just, you increase here, you decrease again. You really stay here with the temperature. So you really stay in the metastable zone. You increase, you decrease. There are very small oscillations if you would represent, let's say, temperature with time. If this will be temperature and this time, you just, and this is your metastable zone width. Let me go back to slide. Yeah. So you would just, temperature with time, you just stay here, actually. And you run, if you can have a broad metastable zone width, not to a very high temperature, because then you might degrade the compound, then you can run even more cycles. And slow.
Thank you. A more basic type of question: how can we differentiate between salt and co-crystal? A question from Sun Pharma.
Yeah. Single crystal, very good question. So single crystal data, I would say, if you have crystals like this, 80-90% of the cases you might be able, you are able actually to see the transfer of proton from, let's say, a coformer to a compound. So you see where the proton is, and if the proton is transferred, then you can say it's an ionic interaction, so it is a salt. If the proton is not transferred, then it is a co-crystal. There are cases, and we have publications about that. Very nice. You are like a detective to see where is this proton. As we know, X-ray is not so, hydrogen is not scattering so well in X-ray. So then a complementary method, and it's beautifully completing the single crystal, is solid state NMR. And there you can very nicely spot, for instance, a nitrogen, and you really see if there is a chemical shift or not, and yeah, you can then say if it is a salt or a co-crystal. But that's an important part, and in many cases, especially with very flexible molecules or crystals which are not so beautiful, then you will need an additional method. Another method that we, in very, let's say, complicated cases, when you have, I don't know how many nitrogens and solid state NMR will not give you the answer, then you can use XPS, X-ray photoelectron spectroscopy, and there on the surface, and there you can really determine that as well. So there are possibilities. Please come to me with a challenging, if you have challenging cases.
Yeah. I think this was one of the first examples that you have mentioned to me when I met you at Avantium. It was a compound of a customer about the salt co-crystal. See, it's coming back, Mihaela. It's beautiful to work again with you.
Yeah, true, because it was in a customer project and we published afterwards. After patenting, it was published, where we found actually it was a form which was a salt and a co-crystal in the same.
Yes, yeah.
And it's a marketed compound. Yeah. Mm-hmm.
What typical heating and cooling rates do you use? How sensitive is the metastable zone width to the cooling rate?
Yeah, we had also, remember, Carmen, we had a study about that, and sometimes may vary. Maybe that's subject of another webinar. Well, we found, I would have to remember, I think 0.1 degrees per minute it was that we stuck with for comparison purpose, but we saw in some cases variation, and we tried to explain scientifically what that would be. But we are still working on that.
Yeah.
But that can be also information, huh?
Yeah, yes. Would there be a morphology change based on steering speed changes? Have you experienced this in your experiments?
To this scale, we didn't vary too much the stirring, only to make sure that it is, a movement, but it is too small scale, I think, we didn't experience that it will make a difference. No.
Questions keep on coming, but I think I will take the last one. My problem statement is a bit of the inverse of the typical goal of crystallization studies. Rather than optimizing or maximizing crystallization, I am looking to understand how to prevent it. That's an interesting one.
Yeah.
I have a neat resin that demonstrates a range of tendencies to solidify, and our customer does not want it to. Keep it liquid. Can you talk about the method development approach to more precisely determine onset across samples of neat resin and accelerate onset in a way that can be correlated? Oof.
So to prevent, what I understand, I didn't understand
to
prevent crystallization.
Yeah,
you can do for instance, you can do an in situ screening with different, I don't know what it is allowed, but an in situ, and to see where it will stay in solution. It's not like an additive, but really, I will need to know more details, what it is allowed in that to keep it liquid, what can you put in there or not. But you could, it's more a formulation, I think. We do, for instance, in situ salt screening to keep it in solution and to increase solubility for IV products, for instance.
Yeah.
But an in situ, and with Crystal16, I think it's good because you really, with the turbidity, you see where it works and not. Yeah.
That's the added value, is the beauty of it. And talking about transmissivity, turbidity, Yogesh is asking about if you have a turbidity, can you have a turbidity check with the Crystal16? Yes, it comes with transmissivity technology. Not completely correct to call it turbidity, but relates a lot to turbidity. Yes, exactly. So yes, Yogesh. And Fabio Souza has another question related to the Crystal16 and if it's possible to seed in the Crystal16. Unfortunately, in the Crystal16, not. But then that's your the crystalline instrument is specifically developed for that, for seeding an anti-solvent or multi-component evaporation and so on. So if you would like to do those type of experiments, then maybe you need to look into the crystalline, which comes
crystalline with visualization as well. I think it's nice.
Yes, exactly. Yeah, yes. This is it. Let's wrap it up here. Thank you very much, Michaela. It's a pleasure, as always, to work with you. I'm happy that we had a chance to work again together, and hopefully we will have more chances in the future. Thank you very much once again. Thank you to all our viewers today, attendees. I hope you all enjoyed it. Stay tuned. We are in February. In March, we have another webinar coming with Dr. Marcus Roden from Delic Labs in US. You will, in a few weeks, see our announcements. Have a good day, afternoon, or evening, everyone.
Bye, everybody. Thank you. Bye.